if you think we don't have enough interesting materials to talk about within the realm of materials engineering, well, I have to tell you that you are probably not right, because today we are going to talk about alloys, and alloys are a really interesting part of part of our society, and also an interesting and complex part of material engineering as a discipline. What you need to know is that before starting this course is that you need to go and watch our course about solutions, because we will use those concepts to talk about alloys. I would put the link, I think, up there for you to go and watch our course about solutions before coming for alloys, because we definitely need it. But the topic of today, alloys. So let's begin with this, that discuss a quick recap that why we are looking at to solutions, to the course of solutions, because alloys are also solutions in solid state. They could also be in liquid state, like we have liquid alloys, but alloys are solid state solution. So in many forms, they are similar to a sugar and water mixture, and that you make a solution the same way we make solutions of other materials, including alloys. So alloys are metal solutions. A definition of an alloy is a solution that at least has one part in form of a metal or as a metal element. So that's a definition of an alloy. It's a mixture, like a solution with at least one part metal. Alloys, they seem, the word and everything seem to be something really new and modern, but it is not so. So if we look at the history a little bit, um, many years ago, we started with Stone Age, right? So Stone Age is started from somewhere between 2.6 million years ago to about 10,000 BCE. That it was Stone Age. We didn't use any kind of a metal. But starting from Bronze Age, like 3000 BCE, it's something about 6,000 years ago, the Bronze Age started. And bronze is an alloy. So from then, like 6,000 years ago, people could extract metals and make alloys of them. And then it was the Bronze Age. And what came after that was the Iron Age, about, let's say, 3,000 years ago was the Iron Age. And iron was also used in different alloyed forms, meaning that other elements were also dissolved in iron during the Iron Age. Different civilization entered and exited each age, like Bronze Age and Iron Age, at a different year or different era, but altogether, that was the transition between Stone Age to Bronze Age and then to Iron Age. What it tells us is that people so long ago were also using alloys, and somehow, without knowing chemistry and physics in the way we know it, they could extract these materials and they could make these alloys. So it's interesting to know, actually to realize that they had a different way of understanding materials and nature around them that was somehow different from our way of understanding, because we are using different, probably, methods and understanding to come to the same conclusion or application, that is like making an alloy. So it is very interesting to, as engineers, to have an open mind and understand there could be different ways of understanding and solving the problems related to the nature, at least the ones that are uh, somehow physical, not metaphysical, like black holes that go beyond our understanding of physics. Okay, that's a history of alloys. It's important for us to know that they're so old, and it's an ancient art. And now with the methods that we have in scientific community and with modern technology, then we can spoil all those um, experiences and knowledges that was before us and also build upon it and make a great materials, advanced materials, materials that people in the past couldn't make because according to what's left from them, we know, yeah, yes, they could make these materials, which is magical. You can't understand without understanding chemistry or physics. How do you do that? And now, but because of the methods that we have, machines that we have, the technology that we have, now we can make really, really advanced materials. So instead of bronze and iron and maybe some iron alloys, now we go to alloys today. The materials that we use today, something that is a link between our past and the modern day are coins. So coins, we use them less and less and less, of course. But coins were at the link between the old ages and the modern ages that we use coin until a few decades ago, um, quite commonly. But leaving that link from the old ages and now we come to really advanced materials. For example, they are advanced alloys that we use in jet engines or turbine blades that we call them self-healing materials. These self-healing materials, as the name kind of entails it, they are materials that after they are cracked, after there's a mechanical failure, a crack initiation somewhere in the blade, in some process, they can re-heal themselves, meaning that they can fill up that crack so that that crack is not there anymore. We can now make those alloys, and there are a lot of research funds these days to work on self-healing materials. So if you look at many universities around the world, in their material or mechanical department, there is at least probably one person working on self-healing materials. Um, think about durability of self-healing materials, a material that when it breaks, it can heal itself. So imagine the durability. Talking about durability, there are also advanced materials developed from aluminium. So if you use aluminium like pure or what we call monolithic aluminium, meaning just aluminium, not alloyed or mixed with anything else, yes, the material is light, but it's not that strong. The strength that we expect from a structural material, aluminium cannot live up to it. But if you alloy aluminium with other elements present on the Earth, like in the periodic table, then you can get a lot of strength and toughness from an aluminium alloy, not monolithic aluminium, which means only one phase, but from an alloy, you can get a lot of additional property that you couldn't get with that metal. The same goes for other metals and elements. So we can now make a lightweight aluminum alloys that are now used in airplane bodies. So in terms of the diversity and application specific designing of alloys, we are now far, far advanced than the old ages, although they've been the people that started with this art of making alloys like that. I think they were mostly working within the framework of alchemy with the highest idea of turning copper to gold. And that was like the holy grail of alchemy that they never achieved. But to get there, they've discovered a lot of physical and chemical phenomenon in that path, which really that's where our chemistry and physics are coming from, the modern chemistry and physics. That's how I think about it. So this is about alloys in the past and alloys now. They are a really, really interesting concept. As I said, alloys are metal-based solutions. They are a mix of at least one part metal. That's what we call alloys. And so if you look at the picture on the right, the same way that you make sugar and water as a solution, that's how you make a melt and you add your materials together and then you either cool it down or heat it up for the mix to get one phase, to get a solution. Also, most of the time, also in these big melting pots, you stir also in some way, either mechanical or using some other way to make your good mix to make an alloy. So you need to mix metals together to get an alloy. And for metals, it's not like sugar. You don't mix it at 20 degrees or 80 degrees. You mix them at 1,000 degrees, 1,500 degrees, depending on the type of metal that we have. For example, aluminium and magnesium, their melting temperature is somewhere around 650, 660 Celsius. So from there, you start to 1,000 degrees, 1,500 degrees to have a melt if you want to make an alloy in liquid phase. So if you want to create your alloy with all the constituents being liquid, like liquid state processing of your alloy, then you have to melt everything beyond their melting temperature, or at least your solvent if you want to do it liquid phase. At least your solvent in the liquid phase to be able to have that kind of a solution. So in many ways, they are just alloys are a solution. So to be able to mix metals together or materials together and make an alloy of them, first of all, we need a host that is our solvent. So that is your base metal like aluminum or magnesium that you want to make an alloy of. So that's your host metal. It's your solvent, the big chunk that's going to take in other elements and materials to make an alloy. So that host needs to provide somehow available room for other alloying elements, solutes, the smaller chunks, to come in and make a solution all together, make a one-phase solution, one together, that is just one. So there are ways that this host can provide available room for alloying elements to come and take a place. One kind of available room that is generally available, thermodynamically stable, and they are always there, are vacancies. That's a natural available space that you can in your host material. So if it's the image on the left, if it's a perfect crystal structure of a host metal, and these gray circles are atoms. So atoms are nicely arranged, looks like a crystalline material because it's ordered. So the atoms are arranged and it's a perfect crystal. Well, perfect crystals don't exist. We can create them in some conditions, some control conditions, but in nature, perfect crystals don't exist. Crystals exist in nature, like naturally and thermodynamically stable, imperfect. So they are always imperfect. How they are imperfect, they have vacancies. So image on the right, look in here. In here, they should have been another circle like that, but it's missing. That's what we call vacancy. So vacancies are these free spaces, these open spaces within the crystal structure, within the crystal structure of a metal that are missing. So there is no atom in here. When you have a missing atom in these places, then you have a vacancy here. That's what we call vacancy. So that is one kind of available space that we have in form of vacancies. As I said, they are by a lot, and they are always available within the crystal structure of your metal. So metals and materials are never this perfect, the image on the left. They always have some vacancies in their crystal structure, meaning that in some places, atoms that should have been there are not there and they're missing, just like this image on the right, just like what we could have had here. Then this empty space, we call it vacancy, and this empty space can provide for the solute atoms that's going to come into our solvent that could provide them some room. For example, this red one, which is an atom of the solute, an alloying element, could could come here and take its space. This one, which is also another alloying element, the second version of alloying element, can also travel to here. So this is just a general available space for anything that can fit in this area that can come in, more or less fitting that can come in. So vacancies are an important part. Second thing, second kind of providing available space is by substitution. So this one is by substitution. Substitution means that for substitution to happen, you need to get rid of a gray one, that you shoot it out, you kick it out, and then one atom of your alloying element of your solute comes back and takes place. So these red ones are substitutional replacements, substitutional alloying. So what happened in these red ones? Same thing. So one gray was kicked out and one orange or red was coming in. That is your alloying element. That's substitutional way. One atom needs to go out of the host for the alloying elements atom to come in. A third way is interstitial alloying. So when there's an interstitial element or alloying element, these are like these ones, these green ones. These don't require the process to kick out one atom of the host. They can just very well fit in between the atoms of the host because their diameter, their atomic radius or diameter is small enough for them to fit in between the atoms. They are ratios of the atomic radius of the host to the atomic radius of the alloying element for them either to be substitutional or interstitial, because as you can see, there's a size limit for interstitial alloying elements. If they're bigger than certain size, that they cannot fit in interstitial spaces, but they're numbers that you can always look up to see what are these sizes for different crystal structures and for different materials. I intentionally don't talk about numbers because their numbers are different for every material. And if you have a material of interest, then you really dig in. You learn it as a target, but you're talking about fundamentals, and that's what's important. Then you understand everything, then you know where to dive in. That's the whole idea. So we have vacancies available. We have substitutional way of alloying materials, and we have interstitial spaces available, which are smaller in terms of size than substitutional, that you get rid of a big atom to fill in. So crystals are also not perfect, but that's what an alloy would look like inside when there's a solution. So that's a solution, that's a pure metal, but pure metal, as I said, they're never like that. Also, even in non-alloyed form, a pure metal will be missing some atoms in these places. So there will be vacancies. As we said before, as the Bronze Age and the Iron Age, there are also these classical alloys that we make as a solution. So now, for example, bronze, now we know is copper as a metal, as a host, and then 12% of tin is added to it, and they made a solution. So in here, our copper is our water, glass of water, and tin is the sugar cube. And then we dissolve them all together. In that case, it makes sweet water. In this case, it makes bronze. That's it. Same case for brass. It's copper as the parent host, and then you mix in 34% of zinc, you make a whole solution. Everything is dissolved, so it's just one, just like a sweet water, and then you make brass. But the brilliance of alloying is that copper has a certain property, but you don't see pure copper used in statues or musical instruments, for example, or other things like copper-based instruments that will be used, for example, in a hospital, for example. But so this bronze statue and this musical instrument, they have copper in common, But we added 12% of tin to the copper. It made it harder and also corrosion resistant. So it's a different property than the copper itself. And then in addition to that, take the copper and you add, instead of tin, zinc to it, and it becomes really soft and malleable. So you can make complex shapes and musical instruments from that with all those little details. But it's much harder to do it with bronze. Bronze is better for statues, and you can also put it outside. It's really resilient, and it's much harder than brass. Brass is softer and more malleable. So with alloying, you can really manipulate the structure and properties of your material. You can make a spectrum of properties when you're alloying with different materials and also with different amounts. So we are certain that if you add in a brass example, if you instead of 34% zinc, if you have 10% zinc, you get a different alloy, right? And therefore you get different properties. So by every percentage, even half a percentage that you're adding each of these alloying elements to your host, to your solvent, you are making a different material. Now imagine the spectrum of materials that you could have. It's like between 1 and 2 is an infinite number. That applies to making alloys as well. So you can really be creative about making alloys. One alloy that is really uh, uh, has played a main role uh, in industrial revolution is steel. So steel, which is an iron carbon alloy, meaning that you have iron as your solvent host, and then you mix carbon to it, and then you mix it until they become one, and they made steel. This steel, which is relatively more modern than all the classical ones that we discuss, especially in its most modern form, we've been making it, uh, for decades. So we have very old steel making factories that kind of look like the modern ones. As you can see in the picture, they are basically doing the same process. Of course, with the knowledge that we have, we're now making much more complex chemistry for our steels that we're making, and the properties are now better, but we still use steel for all those applications. So you use steel, um, look at this, you still use steel for construction, we still use steel for railways, and now we're using a special type of steel for cars, use special type of steel for rockets, for example, for some rockets, also for airplanes. Usually today, airplanes are, they're not, there's no part that is actually probably made of steel, but a lot of rockets still are made of steel. So steel has a big role in our industry, and as material engineers, we need to know about steel because that's one of the fundamental materials that we're using in our industry. So we really need to know about it. Um, to understand steel as an alloy, we need to bring it all its phases into a phase diagram, making an abstract of it to be able to understand it. What phases form how much carbon you dissolve in your iron, and by the percentage of carbon you're adding, what kind of phases do you get at which temperature? Just like the sugar and water, that at which temperature for which composition of sugar you get what. This is the same thing. So instead of sugar, you have carbon, and instead of water, you have iron. Now, for the next video, we want to really bring that into our understanding. So when we look at the phase diagram of iron and carbon, which is steel on the right, as compared to sugar and water on the left for previous course, then we need to look at this as a solution, see at which composition of carbon and at which temperature, what phases do we get, all those supersaturation concepts, can we make a supersaturated steel, and what crystallizes out the supersaturated steel at what temperature. So we're going to really bring all that into our understanding and have an idea how these specific alloy is made, and also try to apply it to other alloys, and also discussing some smart materials and shape memory alloys in the following lectures. I hope you liked it so far. We'll keep the rest for the next video. Goodbye.